Okay, so I'm delighted to introduce our second speaker of the second session, Professor Afaf El-Sagheer from the University of Southampton. And Afaf is going to talk about combined neutral backbones and dendrons for therapeutic oligonucleotides delivery. Thank you, Afaf.
Thank you. Thanks, Muhammad, for the invitation. And I will talk today about delivery of oligonucleotides, therapeutic oligonucleotide. And as maybe many of you know, that delivery of therapeutic oligonucleotide is a bottleneck in the field now. After approving few in the clinical, and I mean more in the clinical now, the challenge is how to reduce the toxicity, which is coming from just like a lot of phosphorothioate, which bind maybe randomly. Second thing is the targeted delivery. Been solved for liver so far by introducing GalNAc, but targeted delivery to other organs is still a challenge. So what I'm thinking is if we combine neutral backbone, which we have some experience with, which will reduce the charge of the therapeutic oligonucleotide, and we know that the cell membrane is negative charge, so we think that reducing this negative charge will improve the uptake, but this will be general uptake. But also we can introduce it as a group, as dendron, because from also literature, if you have like spherical DNA, it might help as well in delivery. We can combine this with targeted delivery by introducing certain ligand at the 5' end or 3' end or internal. So the idea is to introduce the therapeutic modification in, I think this is not working here. Yeah. So the idea is to introduce this neutral backbone as a building block in the cycle of the solid phase oligonucleotide thing. And the more you simplify this, the more you can apply it in kind of general and different applications. So we've done this work before, and we had the amide backbone here. So this was one of our first trial. And what we were hoping to do is to make two monomers. One is the amine, and one is the acid, to form just the amide bond. And if we can introduce this, so we can add the amine as amidite in the solid support, and then have the acid, and we can combine like manually doing the amide bond and get back this to the synthesizer to continue. Hoping that we can automate this in future. We've done this, and with Izzy and Cameron, who were postdoc and PhD student, we've done amide and we've done carbamate as well. And in terms of TM, which is binding for affinity to the RNA target, the messenger RNA target, what we found is that the best one was the LNA amide, when we have the LNA in the top and the bottom. So you have it at the 5' end and the 3' end, meaning that you will have your amine as LNA and you will have your acid as LNA as well. What we found that if we have it at the 5' end or the 3' end alone, they increase the TM, but not as huge as in both sides. We've done crystal structure as well, and we showed that this modification is very similar to the phosphate or the phosphothioate structure, and it didn't kind of change the B structure of DNA. So we introduced this up to 4 times per the modification, and we showed that if you do it by transcription, by transfection, they will behave similar to the phosphothioate oligo. And if you do it gemminotic, which is our aim in the end, if you do it without any transfection agent, you will see that the purple one is our modification, is kind of 5 to 8 times kind of equivalent to the LNA modification alone with the phosphothioate without our modified neutral backbone, or the phosphothioate 2' omethyl only. So we know now that it is better. It was better, I'm not showing the data, but it was better as well as toxicity. So we showed that the neutral backbone less toxic than the phosphothioate. which kind of makes sense because the phosphorothioate, we know that it binds randomly to a protein. There was one disadvantage in this. So it worked very well. We wanted to proceed it to work in addition. So all the work we've done was in kind of reporter assay, which means that we measure the luciferase assay. In this way, it was just ASO. We can choose easily what modification we put. And usually when you start with TT or TC because they are easy to work with rather than A and G. When we wanted to move to the gapmer, and most gapmer will have in the wedges G's and C's. And we thought that, okay, we figured out the chemistry in T's and C's. It should be easy for A and G, but it wasn't. So it is not the length of the senses which was the problem. It is G and A was the problem. So we wanted to move away from this problem. And when I started in Southampton, I started to go back to our simple click chemistry to try to see if we simplified the chemistry and we do triazole, what will happen. This also will give us the chance to make very easy library of LNA in both sides, but also 2' omesyl or MOE in both sides. We wanted to do 1,4 and 1,5 because we believe that the hydrophobicity will be different. And we've done some preliminary work in the 1,4 triazole, and it was similar to the amide. That's why we wanted to do it, because we know it is simpler. So you can just, from buying the LNA, and just in one step, which is alkylation, you can get your monomer. The azide is, again, one step from the OH, which you can buy commercially available as well. But we believe the 1,5 will work better. We didn't do the experiment yet, but we believe it will be better. Right, so this work was done by Nina in my group. In the same time, I wanted to as well check about the phosphate, sulfamate. Sorry, I think from Mac to BC, it changes the resolution. I do apologize about this. I didn't check beforewards because the room was locked, but that's fine. I do apologize for that. So I believe that the sulfamate is very similar to phosphorothioate and phosphate, and I believe it will work better. And so this is the LNA amide results. And I'll show later that the sulfamate really worked better. So we've done the dimer. We couldn't make it as a monomer. We tried, but we couldn't. This work was done by Belma, who was visitor in Oxford here, and Alice. So what we did the dimer as sulfamate, and we checked few backbones, one of them which was the amide, which we've done before. And what we found is that the LNA sulfamate, when you have the LNA in both sides, this is the only one we tested in still the luciferase assay. It was working even better. So the yellow one is the sulfamate, the green one is the amide. And this is genetic results, which means that it is even working better than the amide. And it is simpler to synthesize. So I'll show the synthesis later. It is simpler to synthesize because you can buy all the reagent, all the precursor, you can buy it. Right. I wanted to move from the luciferase assay to application to disease models. And in collaboration with Mark Gregg in Southampton Cancer Center, we are trying now to, instead of targeting messenger RNA, to target microRNA. In microRNA, what we are trying to explore is, can we control cancer? Instead of killing the cancer cells, we kind of manipulate the system that we can do the polarization in the macrophages. In here, what we are doing, we are trying to move from M2 to M1. And M2 and M1 are the macrophages. And one of them will fight cancer, one of them will help cancer. In here, what we are targeting is microRNA 142, 5B. And we believe that from measurement. So we started with just non-modified ASOs, and what we found is that we can really change this polarization to go from M2 to M1 using ASO, which will target this microRNA. And now we will go ahead and introduce the neutral backbone to see if we can really deliver it better than, because at the moment, all the work we are doing using transfixion, just normal transfixion. This is a sequence which will target ASO. And as you can see, there is variety of Gs and Cs and As as well. We want to increase the number of this neutral backbone to see what is the effect if we try to change this neutral backbone. How many shall we add? 50%, 30%, 40%? And is it related to the TM or only related to reducing the neutral backbone? Is it related to the toxicity of the phosphorothioate, or it is binding effect and it just delivered better? So all these questions we still trying to understand and answer. For this, of course, we needed to do all the 4 monomers, or I would say dimers. So we call it monomer because you need to have phosphoramidite here because this is the building block. But we have kind of the sulfamide. This work is by AJ. So now we managed to make all the 4 dimers. I will not bother you with the senses, and apology again for the resolution. So we managed to do, although it looked like very long, but the precursor is the same. So what we managed to do, we choose sequences, which I mean the 5 will have only T as amine, and then we can buy the other one, which is commercially available, which will be G, A, and C, and T. So the 4 will have the same scheme. So you make it once, and then you add this top part. You just buy it as OH, and all you do, you just activate the amine here. So it is simpler than the amide, but of course we are trying to simplify it more later. Once we compare everything, we can decide which one we should go ahead with, and I'll explain this later in detail. This is the GD dimer as well, which worked surprisingly very well. I have to mention that, as I mentioned, we're sticking with T as amine because it is the simplest, and we are changing the 5' end because we can buy all of them. This is the AT dimer as well. And the yield in all of them are really good. And of course, as I mentioned, we are incorporating all the sequences here, and we are ready now to do this experiment with the modified one. We've done it. We know that we can force the polarization to go to produce more M1, which will fight the cancer. So now we need just to modify them with the neutral backbone, and we add kind of modification at the 5' end for targeted delivery. But this is still ongoing work. I mentioned that we need to simplify the chemistry. So we moved away. We simplified it from the amide to the sulfamate and to the triazole 1,4 and 1,5, which seemed to be working similar to the amide, but we didn't compare it yet with the sulfamate. So the idea now is to continue working in, so I started working as well in the phosphonate, which should be simple as well, because what we will do, as Tom mentioned in the morning, you can just make the monomer from commercially available. So this will be the simplest thing you can do. So we will do this for the phosphonate, continue working in the triester for therapeutic application, but for different other application. For this one, what we are working in now is starting to make activated amine, and we will use it as a monomer. So if we can manage to make the triazole and make the sulfamate also as a monomer, not as a dimer. So at the moment, as I said, we are doing everything as a dimer, which in a way is not really great because you need to cover all the sequences. You need 16 dimers. But the simplest thing will be, which we are hoping that the best will be the sulfonate or the phosphonate, the phosphonate or the triester. So far, the chemistry is so robust, so kind of easy to do. However, at the moment, we don't know which one. Everything we've done so far in biology is just luciferase assay. So we don't know really, comparing each other, which one will be the best. So if it turned to be this is the best, then we are lucky. If it turned to be the sulfamate, which I believe, we will try to push it to do it in solid support, meaning that we will pursue the monomer assay rather than the dimer assay. So you will need only 4 monomers. We started with work with Ben and Lillian as PhD student and the Bashis as postdoc in Oxford here. Right. Continuing in this, I wanted to push the delivery part as well. So what we are trying to do now is to simplify the method of doing dendromer. So we started this work. We published short paper in this with Jerry. And in this way, you just make the oligonucleotide in solid support. You change the 5' into azide, which is kind of established. And then you add a linker to join, depend on how arm in your linker, you join them. And surprisingly, it was very efficient method. The yield is not great, but it is very efficient. And if you modify the OH again, you're still in solid support, you modify the OH again to azide, you can really add the same linker again, and then instead of doing trimer now, you can make nanomer. And you can continue. However, the more you do steps, the less kind of yield you have. But we established the methods, and now what we are doing, we are trying to increase the number of the linker to do one step. So instead of doing few steps which reduce the yield, is to make kind of the linker itself with we made these monomers, but or linkers, but the yield is not great with the dimer because you can see that the mixture, but we are trying to optimize the condition now. Right, so testing them with therapeutic oligonucleotide, we started with the luciferase sequence again because it is simple and we know the assay how to work with. So we've done some work. We tried to improve the yield by changing kind of the length of the linker, and also kind of we think that if the distance here is longer or shorter, it might affect the yield. So far, we improved the yield, but it didn't go as well as we hoped. Then we came across this symmetrical one, which improves the yield a lot. So it is simple, it is cheap, you buy it and you make it in one step. And I mean, this is not the best gel, but we improved the yield rather than this now. So you have mixture of trimer and dimer. So we are trying to take the trimer, which will have 3 oligonucleotides here, and we functionalize this for different application. But what we are really doing now, because we tried the one which is close to each other for siRNA, but it didn't work as well as the normal ASO, because you want to have like double-stranded. So we thought this simple one, which I showed before, which is here. So maybe this one, the distance and the flexibility will improve the yield for the siRNA because it is duplex. So we managed to make this, as you can see it in the top. So we managed to do the complement, and we managed to do the luciferase oligo itself. You can anneal it with the complement to have the siRNA. So we tried this for siRNA, but we're still improving the yield. So what I'm planning to do now is, can we build 2D or 3D structure from this? Can we take advantage of the complementary of the DNA to build the structure? And this is still ongoing work because at the moment we have just a streak, so which is predictable. So we are trying to do like kind of nanoparticle from it. So we are trying to ask the question, can we deliver the therapeutic oligonucleotide as a nanoparticle, but it will be mainly DNA? And then what you can do, you can just kind of deliver this and have kind of linkage here, which is can be cleaved inside the cell. Then you deliver your siRNA as a nanostructure or as a nanocompound, and then it should be cleaved inside cells. So this is the ongoing work now, and I'm just hoping that this will work as I am managing. Right. So with this, I want to thank the people who've done the work, who are EJ and Nina. And I want to thank, of course, collaborators from Southampton and here from Oxford. First time for me to put Tom Brown as collaborator. And but yeah, I remember to put his name. And of course, thanks for all the funding bodies. Thank you for your attention.